this. So we are discussing functions. You see that's still pretty much the beginning. And intentionally rather slow. So functions, as I explained yesterday, is something which has a domain. The set of all possible inputs, often denoted by a capital letter, it's a set. And the function itself gets a name. It's usually a lowercase letter. F or G or H are very common letters to denote a function. F, like the word function, so in mathematics we often like shorthands which indicate from where it comes. F for function, X the domain, and we use the arrow to say we have an assignment. Elements from the domain are assigned to elements from the codomain. And in fact, they are only mapped into it. So the elements of the codomain, which are actually images, think in terms of an image getting mapping from here to an image here, are called the range. So the range is the set of all elements in the codomain which are actually taken by the function. So if you think of this function as a table, we started with tables, then the domain would be all the numbers on the top of the table, the range would be all the numbers on the bottom of the table. The codomain can be a little bit bigger. If you think of readings of some measuring devices, then it makes sense to think of the codomain in terms of all possible readings. But the range are the actual readings which occurred in your particular experiment or measurement. So we use this long arrow to show f is a function which starts in the domain X and ends in the codomain Y. Very often our domains are either the number of all real numbers, which makes a lot of sense in mathematics. But in practice, you wouldn't have a domain which is all real numbers, then very often it is just an interval. Maybe closed or not closed, so an interval from A to B. So if you measure over time and your input variable is just time, then you probably start your measurement at a certain time, called A here. I just use letter as a replacement, as a placeholder for any particular time which could here occur where you start and the time where you stop. This shouldn't be difficult. It is a bit abstract, but it is also the purpose of this unit to train your abstract thinking. Mathematics is abstract, which means sometimes it's simpler. We forget about many particular things which would distract. So if we count, and you know, well, counting from early primary school, you know when you count, it doesn't matter what objects you count 1, 2, 3, 4, 5. This is very abstract. This is very much abstract thinking, that you can do this mathematically without thinking what are your particular objects you count. And it's similar in mathematics. Sometimes you find, well, a function is very abstract, but one and the same function can model very different processes in nature. And if you think in an abstract way, you feel this is simpler because you can forget about all these distracting, complicated things in real life. You just have your function. It's very similar as when you count, you forget about what it is you count, you just count. And we want to achieve a similar, command of functions as an abstract model as you have a command of counting as opposed to counting certain objects. So in a sense, what you did in early primary school is maybe it's more difficult than what you do here, but you know it already. So everything what you know is more easy than things you don't know. If you get a bit of practice using these notions, it will be as simple as, say, counting. So for the codomain, we just usually take the set of real numbers and we do not care. We care more about the range than we do about the codomain. So when we have a function from a finite set, then we can use a table, say input x, output y. Here I list my codomain, say -1, 0, 1, 2, something like this. And I have here a 1, a 2, a 2 and a 3, something like this. This table already describes a function with the domain here, the set of -1. So x is the set. Here you see the curly brackets, it's a finite set. I can just list all the elements. And I could make up a codomain here, but as I said, we do not care too much about the codomains. It's more important to talk about the range. The range here is the set of 1, 2, and 3. Yesterday we started talking about inverting a function. If we invert a function, the inverse function is the function which goes the other way around from the bottom to the top. And of course, the domain of this new function can only be the range of the previous function. So in this sense, we have a chance here to find the inverse of 1, 2, and 3. Not of 4, not of 5, because they do not occur in the bottom row. Anything which does not occur in the bottom row cannot be in the domain of the inverse function. By the way, the inverse function is usually denoted by the same letter as the direct function, but with a little superscript -1 on the top. This is the inverse function. It maps, in the best case, the range into our previous domain, into the previous domain of f. So the range of f into the domain of f. But this does not work always, as I explained also yesterday. If we look up in this table, number 2 occurs 2 times, and we don't know which is the right one. 2 is related to 0, 2 is related to 1. I explained it yesterday. If we measure temperature and we want to recover at what time it occurred, if the same temperature has occurred at different times, then we cannot recover the time. So a function where this does not happen, where any input is in relation with exactly one output, the same output cannot occur at different inputs, is called a one-to-one function. One input corresponds exactly to one output, one-to-one function. Or there's also, if you like Latin words, it's also called injective, an injective function or one-to-one function. By the way, there's also a Latin word, if the range is equal to the codomain, then we call this a surjective function, but don't worry about these terms, but I know there are some people who know a lot of this, so you may find it interesting to hear these words. So if the function is one-to-one, which this function is not, then we can invert it. So there is also another notation using a slightly different kind of arrows. When we want to express how a particular value, say -1, is assigned to a +1, we use a slightly different arrow with a dash here. So this arrow with the dash is used to show which particular input is mapped into which particular output, we use the arrow without the dash if we want just to say the function has domain x and codomain y. It works from x into y. So this is between sets, and this is between elements of the set. Or we can say any element, any x, any input is mapped to some output. And there's also another notation which we will use a lot. Actually, we'll use when we work with algebraic formulas, we will use this notation that y is a function f applied to the input x. So as I said yesterday, think of f as any procedure which produces an output for a given input. It could be a calculator button, and you have a lot of functions on your calculator. You give some input, then you press a button for a function and it gives you an output. So in this sense, you can interpret a function as a calculator button. A function can be interpreted as, can sometimes be just an algebraic formula, as I gave you an example last time. And the good thing about algebraic formulas is, instead of working with all these tables, with all these lots of data, you have just one formula. And manipulating this formula can solve a lot of problems for infinitely many inputs and outputs at the same time. Nowadays we have very powerful computers, and we can actually process data from experiments, even if it is a set of thousands, millions, many millions of data. As long as you can feed it into the computer, actually putting it in, it may already be a problem, but if it's fed into the computer, you can use the computer to handle such massive sets of data. You couldn't do this maybe even in 10 years ago, certainly not 50 years ago, not 100 years ago. And this is why before these powerful computers existed, there was no other way than modeling sets of experimental data by a simple function, as simple as possible, by an algebraic formula, and then work with the algebraic formula. Still today, it is a great advantage if you have a formula model for data, and this is why we study this here. In statistics, probably you will more be concerned with these massive sets of data. In calculus, in Math120, we are more concerned with formulas. And there's a lot of advantages still now of formulas. First of all, well, you don't need a computer if you have this kind of formula model. And usually formula models are more transparent and easier to understand. Think of laws in physics, laws in economics, laws which connect one kind of measurable quantity to another kind of measurable quantity. So if you have a formula which expresses this, this is called usually a law, and these laws help us a lot to understand what is going on. So if with a large table of functions, it's hard to understand what is going on, but you still can, say, use a computer to filter out from a huge amount of data some particular properties which you are interested in. So another way to, I said yesterday, to express a function is as a graph in a coordinate system with two number lines. One number line which expresses the inputs, I call it the standard x, and the output y. So I explained it yesterday. You can see the domain of a function in the graph, where the curve starts and where the curve ends. So we have some kind, this is the graph. So it's this. So where it starts and where it ends are the start and the end point of the domain. So this is here an interval, so mostly it will be an interval, so the domain. Now, in order to be a function, as I said yesterday, each input is assigned to exactly one output. We can test it by the so-called vertical line test. So if I put a vertical line through a given input, it should hit the curve only once. And where it hits the curve, this is the output, this is f of x. If I put in x, I go in a vertical line up and down until I hit the curve, and then this will be the corresponding output, f of x. And of course, in order to be able to do so, we should hit the curve only once. So for instance, if you had a curve like this, then doing the vertical line test, we hit the curve too, so this is not a function. This is not a function. So the vertical line test of such a curve shows you that it is not a function. So here it is a function because no matter where we do the vertical line test, we hit the curve only once. So yesterday I showed you how you can produce from a graph, without knowing any formula, without knowing any tables, you can produce a picture of the inverse function. Inverse function is just reverting the roles of x and y. The old output becomes the new input, and the new and the old input becomes the new output. So it's basically making this x and making this y. But this is not how we look usually at a graph in the coordinate system. Usually we want x here, and we want it pointing to the right, and we want y here, and want to point it upwards. So of course we can now do something to this coordinate system which puts the x-axis in the position where we want it, and puts the y-axis in the position they wanted. It is a pretty simple procedure. Namely, we flip it around a certain axis. So think of this straight line passing through the origin of our coordinate system under an angle of 45 degrees. 45 degrees. It's just halving. It's called the bisector because it divides this sector, this quadrant, into two equal pieces. And you flip the whole picture around this, this axis, just rotate it, and you see if we rotate this around, it brings x here and it brings y here. This is exactly what it did. So what does it do to our curve? Nothing to the points which were on the axis. So on this axis, flipping something which is on the axis does not make any change. But here you see it would be the symmetric picture. You think of mirror symmetry. Mirror. This is a mirror. This axis is a mirror, and we want the mirror image. It's maybe not as nice as I would wish it was, but you see the idea that if this red dotted line is a mirror, then if I was a better artist, then the red line would be mirror symmetric to the black line. And that's already the graph of the inverse function. This looks as an inverse function here at this stage. It looks as if the function goes a little bit down and then up again. There's a bit of a rough picture. In this case, the picture also should express this, something like this. So you see here the vertical test does not work. The inverse function is, or what I think would be the graph of the inverse function, is not really the graph of the function. And the reason is that here the vertical test does not hold because the horizontal line test, so flipping around these axes, horizontal becomes vertical, vertical becomes horizontal. So we actually have here, for that output, we have actually several inputs which produce the same outputs. So this is the graph of a function, but not of a one-to-one function. So this is not one-to-one, and we can see that it does not hold the horizontal line test. So horizontal line test means you look at horizontal lines, how many times they hit the curve. If they hit the curve more than one time, then the horizontal line test fails. If we have only one intersection, then the horizontal line test does work, and we have an inverse function, and the graph of that inverse function would be that simple picture. In the first assignment, if someone has looked already at this, there are certain problems where you asked about the domain and the range of a function. So the domain would usually be given, because otherwise it's not a function. If you don't tell, it's like a plant without a root. So if you don't tell where the root is, where the inputs come from, then it's not a function. So the domain would be given. And the domain occurs here in the picture. This is above what you draw the graph. But then you can also read the range from the graph, and this is pretty much what you are supposed to do. So you don't have many algebraic tools at this stage to compute the range, but you can read the range from the graph. So you start at the first point of your graph, and you see the corresponding y value is this. Going by horizontal lines tells you what is the y value. Horizontal lines always to the outputs related. And then you see the curve goes up. And so go your output values go up. That's very good. So up to here. Then you go a little bit back again, which doesn't matter. So something is covered twice here. And as you go, follow the curve, follow the corresponding y values, and everything what is swept out here this is your range. So use pictures, use graphs here to determine the range. This function was almost increasing. You can see it's increasing from it going up. So except for this little part here, where it went again down and then up, it's pretty much increasing. So in this case, the range is an interval, and the bounds of the interval is from the smallest to the biggest. So mostly the ranges will be intervals, and you have just to figure out what is the smallest value attained by the function and what is the biggest value attained by the function. This is very simple. If the function is increasing or decreasing, then it goes from up from the smallest to the biggest value, or for a decreasing function it goes down from the biggest to the smallest. First kind of functions we will discuss in some details are linear function, and linear functions are always either increasing or decreasing, except if they are constant. So this should actually help you. It's quite a lot of practical information which should help you in the first assignment. You will discuss it more in detail in the tutorials. The next topic is about combining functions. Better black. Combining functions and inverse functions. Functions and inverse we did already discuss. So assume you have a function f which takes a certain domain x into a certain codomain y, and we have a function g which takes, say, a certain domain v into a certain domain w. So to keep things simple, we can have a table. Say A is given by a table x, y, say 1, 2, 3, and -1, -2, 5, and G is, say, maps V into W, and say this is -2, -1, -2, -3. Well, no, let's put it in order. Say -2, -1, 0, 1, 2, 3, 4, 5, and we get here 10, 11, 12, 13, 14, 15, 16. So if maybe it's not very realistic, but it could be by not thinking again about x in terms of time and y in terms of temperatures, and then you can have another table which gives you a dependence of something else, say volumes of some solid. The volume changes in terms of temperature. You probably know if it gets warmer, it becomes bigger, colder, it becomes smaller. So say you have another table which tells you the volume of a certain solid independence of temperature. So now if you want to find out how the volume changes in terms of time, you can do it in the following easy way. You put in your time, and I use here this arrow. The function f produces, out of the time, it produces the temperature. So in a time x, we produce the output temperature y, and then we apply another function, the second function g, we apply on the output of the first function, and we get, say, some volume, as an example. And that would be, say, W. So we take the output y of the first function to be the input v of the second function, and then apply another function. So first apply f, then apply g. This is called the composite of the two functions, or the combined function composite of the two functions, first f and then g. And in this case we can do it. So we start with an input 1. The input 1 gives us output -1. And fortunately we can find the output of the first function in the first line of the second function. It does occur here. This allows us to interpret the output here as an input here. So we apply the second function and get 11. So our new function assigns to the time 1 the volume 11 immediately. So if we are interested in the volume, we just combine these two functions and this is what we get. Same thing with 2. The output of the first function is -2. Fortunately, it is also an input of the second function, so our table gives us the necessary information. -2 can be interpreted also as a v, and we get the result 10. So, finally, 3 has output 5. 5 is also in our table. And we have 5 here, and we end up with 17. If I had another table here, say 4 and 7, then I couldn't do that because the output of our first function is not an input, is not here. Is not here, so it does not work. We can only compose functions if the range of the first function is in the domain of the second function. So the composite function only exists if the range of f of the first function we apply is in the domain of the second function. So it's very easy to see here in this table. Composite functions are related to inverse functions. There are more examples like this in the lecture notes. So if this is a bit abstract, if you didn't get all of this, I would recommend going back to the lecture notes, and I'm sure you would understand it then. So if we have the first, some terminology. So if I start with an input f, I apply a function. So applying the function, we always write the symbol of the function at the left of it, and then the argument in parentheses. So this is the function followed by the argument in parentheses. This is the main notation which we will use in this unit. So if we have f and an argument in parentheses, this means the function f has been applied to x. And then we take this as a new input of the function g. So we often will write g of f of x. G of f of x is the composite function of f and g. And because f is somehow inside this argument of g and g is somehow outside, I will often call f as the inside function of the composite, inside function, and g is the outside function. Is the outside function. So if I talk about an inside function and an outside function, this means I'm talking about the composite function where the outside function is applied on the inside function which has been applied before to the argument. So as an example, if the inside function f of x is, say, x plus 1, I take my input variable x and add 1. This is the whole function, very simple function. So defined for any real number to any real number, I can add 1. So this is a function defined for any real number. The range, by the way, is also all real numbers. And as an outside function, say, I should use a different letter here. G of v, or what did I have before? I had v and w, yes, g of v. Say this is v squared. So multiplying the input by itself, the square function, so this is v times v. By the way, for multiplication, I will use the dot in the middle. So this is standard scientific mathematical notation for multiplication, multiplying two terms, putting a midpoint in between. So what would then be the composite function? I start with x plus 1, and this is the output, this is y, which at the same time is the input v for the next function. So I take this output x plus 1 and I square it. So g of f of x in this case has a very simple formula, it's x plus 1 squared. And if you have any experience with algebraic formulas from high school, then you will recognize that pretty much any formula is constructed in this way. You have to do certain things in a certain order. If you want to compute a certain expression, more complicated expression in the calculator, then this is the order in which you do it. Actually, you apply a chain of functions, a composition of different functions. So if someone tells you compute this, then what you need to do, and probably most of you will easily be able to do that, you take x, put whatever x is in your calculator, add 1, and then hit the square button. So what you have done then is actually computed the composition of two functions. And we will, as we learn more functions, we will see more functions, linear functions, quadratic functions, exponential functions, power functions, logarithmic functions, and trigonometric functions. Most of you will have seen this before, some of you probably not. Then with having these so-called elementary functions, we can consider all kinds of compositions, which gives us many, many more functions, and many more functions means more possible models to model data from reality. So often I will write a composite function just like this. Take an argument. The input is often called the argument is the same as input. This is just another word for it. Input is more a word which comes now from modern computer science. They think more in terms of inputs. The old-fashioned mathematical word would be the argument of the function. So you apply the function on the argument and you get out the value of the function. So we will use this kind of notation quite a lot. So as I said, compositions of functions are related to inverse functions. So if I have a function, say 1, 2, 3, 4, 3, 10, and I have another function here, which happens to be the inverse function, 3. So you see actually what I have done here is swapped the upper and the lower line and a little bit reordered, but the order doesn't matter here. And so basically the second line is the inverse function of the first line, and if I now do, I have a function f and I have a function g, if I apply f first and g then, what happens? So g applied on f of x, I get a new function for all inputs for 1, 2, 3. So what happens? So 1 is assigned to 4. I look up 4 in the second table. 4 is assigned to 1. 2 is assigned to 3. 3 is assigned to 2. So 2 is assigned to 2. In W here. 3 is assigned to 10. 10 is assigned to 3. And so as a composition, we got a function which assigns to each element of our original domain just itself. Such a function is a very simple function. It's called the identical function. Identical function. Because it identically maps any input to itself. So if I combine a function which is inverse, I get the identical function. I get a function which does not do anything to the input, it just leaves the input as it is. Also the same happens if I go in the other way. If I apply g first, I can't apply g to x, I apply g to v, and then apply f. So again then, if I apply 3 to 2, and then g to 3, I get 2, 2, I apply f, I get 3. So I have 3 to 2, 4 to 1, and 1 to 4, so 4 to 4, and 10 to 3, 3 to 10, so I get 10 to 10. So this is also an identical function, g followed by f. This composition with g inside function, f outside function, is the identical function defined on the domain of g, and f followed by g in this order, first f then g, is the identical function defined on the domain of f. So inverse functions undo what the function did. So this is what means inverse. We undo what we did previously, and this is particularly useful when we solve equations. So most of the equations, they start with a very simple equation, x plus 2 equals 0. Very simple equation. So what does it mean? We did something to a number x which we don't know. X is here a placeholder for a number which we don't know. We did something to x, which means we have applied a function to x, and we know that the result of this function is 0. So this function here, which we have applied to x, was just a very simple function adding 2. So what we need to get our x back, we want an identical function. We want to isolate x on its own, x equals something. So we have to undo, we have to find the inverse function. So what would be the inverse function of adding 2? The inverse function is subtracting 2, so we can subtract 2 at both sides. We have to apply this inverse function to both sides. So we subtract 2 here, we get x, and we subtract 2 here, we get 2. So we get x on its own equals minus 2. This is the solution of this equation, a very simple equation on purpose. It's just to explain you. We undo a function which we have applied previously, and this gives us the solution. So more general equations would look like this. We have a function, f applied to x equals 0, or here could be also another number. So what we do is to apply the inverse function to both sides, if it exists. So, well, of course we can only do this if f to the minus 1 exists. Otherwise we are in trouble, we can't apply it. So apply f to the minus 1, so we apply f to the minus 1 to f of x, and we apply also on the other side f to the minus 1 of 0. So here, as I said, applying the inverse to the function, composing them, means undoing what f does. So this leaves us with x on its own, isolated on the left-hand side. And the solution would be the inverse function applied on the particular input 0. So if we have an inverse function, we just apply it to the left-hand side, or even if we had, say, any number, we could have here 1 or 3 or just some number a, then we would here have f to the minus 1 of 3 or f to the minus 1, where a is a placeholder for any number we could imagine. So if this inverse function exists and 0 or whatever number is here is in the domain of the inverse function, then this would be a very easy way to solve the equation. And this is the reason why we will discuss inverse functions of all the elementary functions. So our program, which I start tomorrow, starting with linear functions, is to systematically study all kind of so-called elementary functions, and we will look at these functions. What is their graph? What's their range? Are they invertible? What is their inverse? And this will allow us to solve equations and to see also for what kind of data the model would be appropriate. So that's probably all for today. Then see you tomorrow for the last lecture this week.